G'day guys, welcome to lecture 2 of topic 2, projectile motion. Here is your learning intention and success criteria. Please complete the KS table down on the side there. Pause the video while you complete this. Okay, hopefully in terms of knowledge you recognise that the recall criteria is a knowledge-based criteria, so you need to know, well, what does it mean for components to be independent of each other. Remember we've talked about that in previous videos, but we need to recognise it in questions now. We've also got a calculate there. Now, we've already done that calculate before, calculating horizontal and vertical components of projectile motion. It is about vectors, so it's going to be similar to what we did in the last video. And then finally, well, we've got that solve, and that comes under a skill. Can we solve some questions about this? Now, I do have a feeling this is going to be a reasonably long video, as I do have a few examples I want to work through, so you've got a video reference to refer to for your own study. So, you know, sort of settle down because you've got a little bit of work on this one. So, projectile motion is when an object moves in both a horizontal and vertical motion, and there has to be an acceleration acting in one of those directions. If neither had an acceleration, it'd just move in a straight line. Yes, it might move off at an angle, but it's still just a straight line. So it describes something where it is being accelerated in one direction while also moving in another. Normally this means things go up, they fall back down, and it describes the path of balls being kicked or thrown, bullets and arrows in the air, water arcing from a hose, anything that moves by flying. Now the text collects projectile motion into two groups, and a horizontal projection and projection at an angle. They look like this. Here we have horizontal projection, something being shot off the edge of something, and here we have projection at an angle. This would be like throwing a rock off the side of a cliff. This would be something like kicking a soccer ball. I like to consider two other ones, and that is when you land on an alternate height from where you started. This is technically landing on an alternate height, but because this is a very simple situation, it's not really that complex. This one we launch and land on the same height. This is what I mean by when we land on an alternate height, either being shot up in the air and falling lower, or being shot up in the air and landing higher. Okay, and I feel these two are fairly complex situations. This one is probably the most complex. So before we get started with projectile motion, we need to remember a few assumptions. And the first to remember is that all of this is happening in a vacuum. In reality, air is pushing back against the thing moving. They have little collisions with the air particles. But to deal with that math, it makes things a bit more complicated. So for the syllabus level, we ignore it. And so that means objects do not accelerate in the horizontal direction. That's our first assumption. Okay, but objects in the vertical direction do accelerate due to gravity, because gravity is going to pull it down. And the text calls this g equals 9.8. Note, the text will not say that it's negative or positive. You have to figure that out for whatever your question is. Now, the second major assumption that we have here is that horizontal movement is entirely independent of vertical movement. And this was discussed in video 2.1. You've seen some pictures of it, and there's also a video on eLearn that shows this in action. So if you're still not getting that, you've really got to go and dig into it. Okay. Now the text defines variables in a new way compared to what we did in our linear motion unit, and each value is given a subscript letter x or letter y, and so this represents if things are horizontal, the x component, or if they are vertical, the y component, and so that is important so you can keep track of things. Now the thing is, projectile motion, apart from some basic understanding questions like you'll see in your Check Your Learning, it's all about problem solving. So the way I'm going to show this to you is to do some problems, and so you can see how these things are done. So let's have a look at our first example. So I've put together examples 1.2 A to C here. So this is sort of a multi-step problem where they've actually asked us each of the steps. So let's have a read here. We have a golf ball is projected horizontally. Off a cliff at 20 meters per second, it takes 4 seconds to reach the ground. Calculate how far out from the base of the cliff the ball will land. So there's the first bit. Now there's some other stuff here, but until we do this first bit, generally we won't be able to do the others. So I'm not going to even bother reading them. Let's do a quick sketch. We have a cliff. We don't know how high it is. We know that its initial velocity that way, horizontal, is equal to 20 meters per second. And we know that the time it takes to go down to the ground is 4. Okay. Now I'm going to use a SUVAT table here. S-U-V-A-T. And I'm going to identify my X values and my Y values. So I'm told that in terms of displacement in X, I don't know that. That's the distance from here to here. But I can work that out. I'm told that the time is equal to 4. And it's also the same time it took to go left to right as it did to fall down. So I can put 4 in both columns here. If I know a time, it's the time of the entire flight, it's going to go into both. I do know that the initial velocity X direction is equal to 20. Because it's going horizontally. And I also know the initial velocity of my Y is 0 because it's all X. It's nothing going up and down. So I'm going to put 0 there. Now if we remember back to our assumptions, we will recall that acceleration in the X direction is equal to 0. There is no acceleration there, which makes that this must also be equal to 20 because the velocity is not going to change. Finally, our Y direction here, we don't know what its final velocity is going to be yet. But we do know that its gravity is going to be equal to 9.8. Now I'm going to go negative 9.8 just because I like to let down be equal to negative. Acceleration acts down, let's make it negative 9.8, that we don't have to think about it. The first thing the question is asking, how far from the base of the cliff? That's our S of x. So Sx is equal to, well, what's our formula for, we have a u, we have a v, they're the same thing, we have a t. So there's only ever going to be one formula we use for this column, and that is that v in the x direction equals s in the x direction divided by t. So wonky looking s, let's get rid of that. S. Okay, and so if we rearrange that, we get that s of x is equal to v of x times t. We know v, it's equal to 20. We know t, it's equal to 4. And so it will end up going 80 meters away from the cliff. Okay. Let's have a look at the second question. The question is asking, what is the impact velocity in the vertical direction? What is this v value equal to? Now, we've worked out that it goes 80 meters to the left. But none of this matters now, because we are asking what is something in the y direction. We can only use our values in the y component to work that out. Now, we have u, it's 0. We have v, that's what we're after. We have a, negative 9.8. We have t, it's 4. And so if I think about it, I know that my formula v equals u plus at. Now, the problem is the text does not write it like this, and the syllabus doesn't either. It will write it as vy equals gt plus uy. It swapped these two around. I don't know why. I think that's a bit silly. Pardon me. And instead of writing a, we've got g for gravity. So this is the formula that appears in your work booklet. It is the same formula as what you did with linear velocity, just we have some subscript y's, and they decided to be extra fancy, swap it around and put a g instead of an a. It, to me, is stupid. But that's what the syllabus is, so we need to be aware of what it says so that we can deal with its stupidities. Let's do our substitutions. Vy, we don't know, that's what we're trying to find. G is equal to negative 9.8. T is equal to 4. And u of y is equal to 0 because it was thrown horizontally. There was no initial, sorry, it was projected horizontally, probably hit with a golf club. There was no initial vertical height. 4 times 9.8 should be equal to, let's see, 4 times 9 is 36. 8 times 4 is equal to 32, so it should be equal to negative 39.2 meters per second. Now, why the negative? We said that negative was down. This ball is going to be falling down. so its velocity must be negative 39.2 down. Okay, so that's why that negative is there. Now we're going to work out the height of the cliff. We want to know what is this S in the Y direction. Okay, so again, we've got S, well, that's what we're after. We've got U, it's 0. We've just worked out V. We've got A and we've got T. Now I'm quite partial on this. I've got S, U, A and T. I don't want to use the V because I've just calculated it. While this is an exact number based off this, I don't like to risk error. So I'm going to use SY equals, and again, the text and the syllabus rearranges the equation. Half GT squared plus UYT. Note, this is the same thing as S equals UT plus a half AT squared. But again, they replaced A with G. U now has a UY. S now has an SY because we're talking about in the Y, the vertical component. And then they swap the two pieces around. Don't know why. Might help you see that this is a quadratic down the track. Perhaps that's why. So we need to find SY. SY is equal to half times 9.8, or negative 9.8, sorry, I should say, times 4 squared plus, now U of Y is equal to 0, and remember anything times 0 is just 0, so that is going to cancel. Half of 9.8 is equal to 4.9, or negative 4.9 I should say. 4 squared is equal to 16, so we have 4.9 times 16, which should be, let's see, nearish 80 meters. So negative 4.9 times 16 is 78, or negative 78.4. Negative 78.4 meters. Now the thing is, it is asked for the height of the cliff. Height is a scalar quantity, so we would just say the height is equal to 78.4 meters. The negative here is telling us how far the ball fell downwards. Okay, so you do have to be aware of that. Now the last part of this question, and I'm going to just get rid of this bit off here, is asking what is the resultant velocity or resultant impact velocity. Okay, but didn't we just work that out? We worked out the impact velocity in the vertical direction. The resultant impact velocity, remember, we need to combine our two velocity vectors together. So we need to combine this initial velocity of 20 with this final velocity falling down, because when it hits the ground, it's going to be both vectors that are part of this. So let's draw that. I have a vector to the side of 20, and I have a vector going down of 39.2. They are perpendicular to each other, they are at right angles. So let's draw that. My resultant is always from start to finish, and we can see that there is a nice right angle triangle here. I'm going to need to work out my angle as well. So let's work out the size first. The size, we'll call this V. V is going to equal the square root of 39.2 squared plus 20 squared. Now I have just jumped right to the end there. That's all the working you really need to show. And you might go, Mr. Warren, why didn't you put the negative in? And that is because 39.2 squared and negative 39.2 squared are the same thing. The negative gets cancelled, remember. A negative times a negative is a positive. So I'm just avoiding it because I don't need to worry about it. And that gives us an answer of 44.01, but being as this only has two significant figures in it, I'm going to say that velocity equals 44 meters per second. And remember, to work out the angle, we need the arctan, tan to the negative 1. This is equal to theta. I'm very much running out of space. Of opposite, 39.2 over adjacent, 20. Let's work that out. 39.2 divided by 20. Take the arctan of that answer. We get about 63 degrees. 63 degrees, and that would be 63 degrees declination. It would be down into the ground. You generally, when you're dealing with up and down type stuff, I don't know if they're going to have a U and a D type thing and you just circle which one is which, but they might just say, deck or ascension, ASC for ascension. I'm honestly not sure on what their sort of responses might be there. Well, they might expect you to write it 63 degrees down in this case, or 63 degrees declination. Okay. Let's have a look at the next one. And the next one seems really much simpler. A rock thrown horizontally at a speed of 35 meters per second off a cliff 75 meters high. Determine the impact velocity. We can see, well, that's just asking for the same last thing we just did a second ago. So let's have a look. Oops, sorry, I forgot to change to my marker pen. Let's draw a picture. This cliff is 75 meters, and the initial velocity is equal to 35. Let's do our SUVAT table. I'm going to do it a bit smaller up here so that I don't run out of room. Oops, A should not be capital. A-T. Okay, X and Y. We don't know its X component, but we do know that its height it's going to fall is 75. We know its initial velocity X is equal to 35, and its Y is 0 because it's horizontal. We don't know this. We know that this is equal to, also equal to 35, because we know that acceleration is equal to 0. We've said that this is positive 75, so I'm going to have to make this, if I make this a negative 9.8, I'm going to get a clash somewhere. So I have to make sure that this is negative because it's the same direction. The ball starts here and goes down, or the rock starts here and goes down. And we don't know the time. Okay, so let's start off with looking at the Y components, because we're going to need to know what is the time to bring it over here, and we're going to need to know what is the V because we need the impact velocity. We have S, we have U, and we have A. So we know that V squared equals U squared plus 2AS. The text changes this to VY squared equals UY squared plus 2GSY, and I think they even swapped this around. Again, a bit ridiculous. Let's do our substitutions. Vy squared equals, well, U is 0, so that's going to go away. 2 times 9.8, or negative 9.8 I should say, times negative 75. Let's work that out. So V, or Vy, is going to equal 2 times 9.8 times 75, and the negative times the negative cancel, so I'm not going to worry about those. I take the square root of that. Now, something to keep in mind is that square roots have two answers. This is giving me plus or minus 38.3 meters per second. And that is because this thing, as it falls down, remember, these things are symmetrical, so we could have gone back this way and found out that at this point here it had an initial velocity up of 3.8, but here it's got a velocity down of 3.8 because we want to care about what it is hitting the ground. So in this case we're only after the negative answer, and so we would only worry about writing the negative answer, negative 3.8. If you wrote the positive you would get it wrong, so be careful with that. Okay, we've got our velocity, so that's good. We can work out the in fact, that's all we need. We don't need to worry about time. We're not asked to work out how far does it go. We only work out the impact velocity. So that means we can now do our two velocities together. We know that originally it had a value of 35, and down here it had a value of 38.3. We can add those together, and so V will equal the square root of 35 squared plus 38.3 squared equals 35 squared plus 38.3 squared. Take the square root of that. We get about 51.9 meters per second. We can work out the angle. So the angle, okay, this angle in here is going to equal the arctan of opposite 38.3 over adjacent 35. 38.3 divided by 35. Take the arctan of that. Oops, what did I do then? 38.3 divided by 35. 35. Yep. Take the arctan of that answer. We get 47.6 degrees. Okay, and so that's 47.6 degrees down. Okay, so that gives us this sort of problem solving. Let's have a look at the next type of part. So I didn't animate that very well, apologies. So when we do projection and angle, it can be represented like this. I want you to have a look at this picture very carefully. What we can see here is that the initial velocity upwards is getting smaller, smaller, 0, changes direction, gets bigger and bigger. In contrast, the horizontal velocity is always the same size. Okay, so this tells us two things. One, the launch velocity will be the landing velocity. Uy and Vy, same size, different direction. Ux and Vx, same size, same direction. That means only the angle will change. The other really important bit is that this is symmetrical, so the time it takes to reach our maximum height here is also going to be the time it takes to fall down from that height. And so the total flight time to go from launch all the way to landing is going to be twice as much as the time it takes to get here, or time to reach max height is half the total time of flight. With these two things, we're able to do a lot of working out from this now. Okay. Remember, there is no acceleration in the x component. That's why these are all the same. It's that first assumption we were talking about. So, let's have a look at this first example. A bullet was fired from a rifle at 200 meters per second at an angle of 40 degrees to the ground. Ignore air resistance. Remember, we're ignoring air resistance. Apologies, that's a little bit unclear, but you can see that. Let's see if I can bring this up just to help you read that a bit easier. Okay, ignoring air, so we can see that a bit clearer. I'll drop it in a second. Ignoring air resistance, calculate the following things: initial vertical and horizontal, maximum height reached, and time of flight, as well as horizontal range. So I apologize, it's a bit fuzzy. I was trying to zoom it in a bit. So let's first off draw. Get that cord out of the way. Let's start off first by drawing what this would look like. It is fired at an angle, so just angle of 40 degrees, and the velocity equals 200. And we want to know, well, firstly, what are the initial and final initial velocities of the velocity, initial parts of the velocity, maximum height, how high did it go? Call that xy max. We want to know the time of flight, and we want to know the horizontal range, how far did it go? Okay, so there's a few things there we need to work out. Let's start off with this. So, to initial vertical and horizontal components, we have the initial velocity, but we don't know how much of it is to the horizontal, how much is the vertical. This is vector decomposition. This is, sorry, vector resolution is the terminology the textbook uses. I've got to get that right. So this is vector resolution. We practiced it in the last video. Let's draw that. We have 200, 40 degrees. We need its u in the x, and we need its u in the y. X here is adjacent, so that means ux will equal 200 cosine 40, and u in the y will equal 200 sine of 40. We can work those two out. 200 cos 40, 153. I'm just going to round it off to the nearest whole number. And 200 sine 40, 129. Okay, we have our initial velocities. First one, tick. Maximum height reached. Okay, so we want to know what is its maximum height. And remember, as we saw in the picture before, when we're going for maximum height, we need to let velocity in the y direction equal 0. So we're going to have Vy equals 0. We have Uy, which we just worked out, 129. And we know acceleration in the y equals negative 9.8. Really important to get these two in the right direction, because if we had positive 9.8, we'd be saying that this speeds up and this would never happen. And we want to work out, well, what is the s in the y at this point? one equation stands out, v squared equals u squared plus 2as. While I know that the textbook and syllabus uses the stupid manipulated ones, I think it's stupid. You're not going to get marked down if you don't do it with those notations. If you would prefer to use the linear notation, please do. If you prefer to use their notation, do that. But I've just been using the linear notation for 20 odd years, so it is just so much easier for me to do it that way, and that's that way I don't have to remember twice as many formulas. So let's put our substitution in. 0 equals 129 squared plus 2 times negative 9.8 times s. And the reason here we can see the negative, when I take this to the other side, or I take this to the other side, this would become negative, and so then I would have a negative divided by a negative. They'd cancel. That's good. My s would then be positive. Or if I take that and divide it back, again the negative will cancel. Rearranging that, s will equal 129 squared over 2 times 9.8. 129 squared divided by 19.6 gives us 849. Yep, that's right. Equals 849 meters. You might go, wow, that seems really high. That's almost a kilometer. But I mean, you are shooting a rifle like nearly at a 45-degree angle. That's a lot of speed. So we have our maximum height. Okay. Time of flight is an interesting one. There's a couple of ways of doing this, and I'm going to show you both. Because the second way, while we can use the doubling of the middle velocity, I actually didn't write those two down. We have 129 and I believe it was 153 were our two velocities. If it's not, I do apologise. Just have to make do. So time of flight, let's work out firstly the time it takes to get to its maximum, and then we can just divide by 2. So if we go with v equals 0, u equals 129, a equals negative 9.8, and t equals unknown, well, we can see v equals u plus at, 0 equals 129 plus negative 9.8t, so t is going to equal, we rearrange it, 129 over 9.8, 129 divided by 9.8, 13.2 seconds. 13.2 seconds, so therefore 26.4 seconds total. Okay, because remember, the time to hit maximum will be the time, twice the time, or half the time it takes for the whole flight, because it is symmetrical. But the other thing about it when it comes back down to the ground is there's another assumption we can make. And we can go, well, what about when sy equals 0? Again, we have vy equals 129. We have ay equals negative 9.8. What's really cool though is that, sorry, that shouldn't be v, that should be a u. Because we know that these are symmetrical, we know that vy will equal negative. Oh, sorry, no, we don't want vy. We can use this though, negative 129. But we want to know t. So I'm not actually going to use the vy. We don't need that. I'm going to just use this, so t. Well, what formula has that? That's our s equals ut plus half at squared. You might go, Mr. Warren, that means we're going to have a parabola. That's so much harder than dealing with this. We're not, and the secret is with this 0. S equals ut plus a half at squared. 0 equals 129t plus a half negative 9.8t squared. We have here a 0. So that means we can cancel some stuff. We have a t is the lowest common factor between both. There might be a number, so I don't care, but there is a t that is a common factor, so I can factorize that out. And I will show you something that is really, really powerful here. Sorry, I know my working is going all over the place and I have to keep rubbing it out. I do apologise. It's just one of the limitations of this style of system, I guess. Might have to look at, perhaps doing this in OneNote so then we can just keep scrolling and make it a bit easier. So that means 0 equals t outside of 129 plus negative 19.6 t. We have a really interesting sum here. This times this equals 0. What's the rule for when two things multiply and equal 0? One of those had to be 0. Therefore, t equals 0, or 129 minus 19.6 t equals 0. Doesn't that just look like the formula we had a second ago? U, A, and T. And there's V on the other side. Okay, and so if we, not quite, because before we had A, the actual value of A. Here we've got two lots of A, and so we're going to get the final answer for T here. So if we then solve this, we're going to get that T will equal 129 divided by 19.6. Let's work out what that is. 129 divided by 19.6. Could help if I could actually read my own math. I've made a mistake here. That's half of 9.8, not 2 times 9.8. So this is not 19.6, and hopefully you picked that up and you were yelling at me through the screen. That is 4.9. Now, the reason I knew that is because I looked at my calculator and went, that's the wrong answer, or that's the wrong number, and hopefully you heard that pause and maybe you had a little chuckle to yourself going, Mr. Warren recognised he made a mistake. 129 divided by 4.9 gives me the answer of 26.32 or 26.3. And you notice that this one is off compared to the other one by, I believe, 1/10 of a second. And that's because this method is slightly more accurate than the other method because there's less error involved in it. So you can use this as quite a nifty trick. So time of flight, 26.3. Tick. Last question for this one, horizontal range. We do have one more example after this. I did warn you, unfortunately, this is going to be a longish video. So the last one we have is that we need to work out the horizontal range. Good news is we've already got all the components we need. We know that ux is equal to 153. We know that the time it takes is equal to 26.3. because time is the only thing that connects between the two systems, as I've said before. And so we can work out that s of x is going to equal u of x times t equals 153 times 26.3 is equal to 153 times 26.3, 4,023 meters. And 4 kilometers, that's pretty far. Not only does it go 800 meters up in the air, it also goes 4,000 meters horizontally in total. Okay, so this is projection when it's on the same height. The other example we have here is when something is not on the same height. So a cannon is fired from the edge of a cliff, which is 60 meters above the sea. We can see that there. The initial velocity is 88.3. It is fired at an angle of 34.5. Determine these things: how long's in the air, the impact velocity, and how far from the cliff. Now, this last bit is going to be the easiest bit once we know its horizontal movement and how long it's in the air. So we're going to need this bit to work out this. And to work out this, we're going to need to work out our two velocities, and that will give us that there. So let's break this down a little bit. There are multiple ways of doing this. One way of doing this is to go, well, we can treat it as shooting up into the air. Sorry, forgot my pen. We can treat it as shooting up into the air and then just work out the second bit like horizontal projection. Or we could treat it as, well, it's a parabola to here, and then we just have something falling with an initial velocity downwards as well, which is pretty similar to something just being pushed off the side of something. Or we can do it all in one system. Now, The other two simpler ones are longer. I'm going to do the slightly more complicated one here because it is faster. If you wish to help with the other ones, and I believe that that's how Walding does in the text, have a look at that and come and see me, and we will work it out together. But let's try it with a slightly more complicated way. We know that it has an a in the y direction of equal to negative 9.8. We know its initial velocity in the y direction, sorry, that should be a u, its initial velocity in the y direction, and we've seen in previous, so I'm just going to skip straight to the answer for it, is going to be equal to 88.3 sine of 34.5, and it's positive because it's going up. We know that its displacement in the y is equal to negative 60 because it is falling down. We want to know what is its t. Okay, and we're also going to need to know what is its v in the y direction for our next bit. So, using this, we can see for this first one, we can use the s equals ut plus half at squared formula. And then for the second one, we could use v squared equals u squared plus 2as, or we could use, once we've got t, v equals u plus at. So let's work out the t first. S equals ut plus a half at squared. Negative 60, got to be careful with that negative, equals, let's resolve that first, 88.3 sine 34.5, very weird number to choose, it's pretty close to 50. 50t plus half negative 9.8 t squared. Let's just turn that into negative 4.9 because I can't be bothered dealing with lots of random stuff everywhere. Okay, we can't use the factoring technique we had before because we have a 60 there. So I'm going to need to turn this into a quadratic. 0 equals negative 4.9 t squared plus 50t, I wonder if you heard my cats just then, plus 60. We've got this here. I could divide everything by 4.9, but there's not a common factor, so it's really not going to help too much here. We're just going to have to use the quadratic equation, and that is probably the hardest amount of math you have to do in this course, where you need to use the quadratic equation. Remember, quadratic equation, this is my a term, this is my b term, this is my c term. Negative b plus or minus square root b squared minus 4ac over 2a. Please note, this will not be given to you on exams. Okay, it does not appear in the text sheet, and to me, I doubt it would appear on a question either, in terms of saying that, oh yeah, remember, you know the quadratic equation and it's this. You can consider it a little bit unfair, but this isn't. But at the same time, there are other ways to do this without using quadratic. So I believe that's the approach they're taking with it. Let's chuck that in. Negative 50 plus minus square root of 50 squared minus 4 times negative 4.9 times 60 over 2 times negative 4.9. So what I'm going to do is I'm going to resolve each of these one at a time. This becomes negative 9.8. The bit in the brackets, 50 squared, the minus and the minus will cancel, so I'm just going to plus 4.9 times 4 times 60, and I need to take the square root of all that. That gives me 60.6. That's good. If this was a negative and we're trying to square root a negative and we've got an error, that would tell us that this done something very, very wrong. Generally means when you've put a negative where there should be a positive. And let's work out what these two possible answers could be, because this plus minus means we're going to have two possible answers. Negative 50 plus 60.6 divided by negative 9.8. Now the fact that this answer is negative, negative 1.08, is important. We cannot ignore that. Or negative 50 minus 60.6 divided by negative 9.8. 11.3 seconds. So we need to choose which one of these is the correct. Now obviously positive is the correct one, but why is it the correct one? Why do we have this one? What does this one mean? This one means that if we were to take this back and turn it into a parabola starting at the same level, when it was down here, or if it was, you know, to trace back down to here, so about there, okay, that would have happened 1.08 seconds before it got to there if it was shot at whatever the initial velocity would be. So that 11.3 is our right answer, but that 1.8 has meaning, and it is good for us to know. Okay, I'm going to have to get rid of all this. Apologies. We've got 2 parts of this problem left to go. Unfortunately, I don't believe there's an easy way for me to just select it all and then clear it out, so we have to suffer through this. Okay, second part, we need our Vy. I'm going to use the v squared equals u squared plus 2as, because again, there is less error. I said that was equal to 50, didn't I? So, v squared equals u squared plus 2as. V squared equals 50 squared plus 2 times negative 9.8 times negative 60. So the negatives will cancel, which makes sense because I expect this to be bigger than this because it's going to increase in size. Alright, let's plug this in. 50 squared plus 2. The negatives will cancel, so let's ignore those. 9.8 times 60 equals... Now we have to take the square root of that. V squared equals 76. And that means V is equal... Remember though, 60.6. Hey, didn't we just see that number a second ago? The excuse me, this is the same thing as the determinant. This is my b squared minus 4ac in there. It's something that pops up quite a bit, so you'll learn to recognize some of these little tricks. 60.6 meters per second, or negative 60.6 meters per second. So which is the right one? This is going down, it's falling into the water. That tells me this one is the correct. This one is what it was when it was back over here. Remember we talked about the time, how the negative 1.08 meant it was, you know, it could start over here and do the same path. Well, it would have been shot upwards at 60.6 here, which means it has negative 60.6 here. Okay, so this is my correct answer. But that's not my full thing. So V in the Y equals negative 60.6. But we need the impact velocity. We need to know its X component as well. So my V in the X was equal to 88.3 cosine of 34.5. Which equals, let's work that out, 88.3 cosine 34.5 gives us 72.8. Okay, and that's good because we're going to need that in a second. Let's go and draw our... Actually, let's erase all this. I feel like I should have some music playing. Let's add these vectors together because that's how we do it. We need a total velocity. We add our vectors together. It doesn't matter which way we do. I'm going to do y first this time. So 60.6 down and 72.8 across. So there's our final velocity, and we're going to need this angle. Now the thing is though, when we do angle, we need the angle it makes with the ground, so we're going to need that angle. Okay, that's why I generally do horizontal first, just because it forces me to always get that angle. This angle would not be the right one. If you said this angle counterclockwise from vertical, or this angle upwards from vertical, or vertically down, you'd be able to get your way through it, but it's a lot easier just to go, what's the angle with the ground? Where's the ground? The ground is going to be here, so let's use that number. V square triangle, this triangle, we know this, square root 60.6 squared plus 72.8 squared. 60.6 squared plus 72.8 squared, and I take the square root of the answer, gives me a final velocity of 94.7 meters per second. The angle is going to equal the arctan of 60.6 opposite over adjacent, 72.8, 60.6 divided by 72.8. I take the arctan of that and I get 39.8 degrees. Okay, now that's that angle in there. Sorry, cat's growling at something. So we have here our angle. Now we need to work out the horizontal distance. I'm going to get rid of all these y values. We don't need this for this last bit because horizontal, remember, is x. Good news is this is a lot easier to work out. So this is like a little, give me an extra couple of points right at the end of the question. Get rid of that. Okay. Horizontal distance, s of x. We know there is no acceleration in the horizontal direction. So based off our formula, s of x will equal v in the x times t. We know t, we worked it out before. We know v of x, we just worked it out a second ago. So this is just going to be 72.8 times 11.3. 72.8 times 11.3 gives us an answer of 822.6 meters. Okay, so that last step, nice and straightforward and simple, but a lot of the rest of it, that is fairly complex. These are challenging questions. Okay, expect to have a bit of difficulty. You've got to slog through them and you'll be able to figure them out. As long as you remember to take it step by step, think about what assumptions you have to make, you will get through it okay, but it is going to be tricky. Okay. Now there is a reference to a question about landing at a higher height. It says it's in the Check Your Learning, but I couldn't find it. I did find it in the chapter revision questions. You might want to take a stab at that. That is a pretty tricky one. That being said, we will use these chapter revision questions as we get closer to exam time at the end of the year, because I have a feeling the exam, then again I'm writing it I guess for the first year, but even when we get it from QCAA in future years, it will have a lot of calculation style stuff. So let's recap. In this video we've learnt the following. We have utilized how horizontal and vertical vectors are independent of each other. We've resolved and calculated the resultant vectors in projectile motion, and we've seen the 3 different templates for projectile motion. Okay, success criteria there at the bottom. For your entrance slip, this is a bit of a big one, sorry, but please access your O-Book, download chapter 1.2 and 1.3 Check Your Learning PDFs. Complete questions 1 to 7 from 1.2 and questions 1 to 6 from 1.3. Now remember, this is in the Unit 3-4 text. Copy your answers into the 2.2 space on eLearn, please. Thanks for listening. Long video. Great work, guys. Catch you next time. Bye.